Hello, welcome to this Matlab video tutorial. Today's lecture is concerned with numerical integration. In the previous video, we introduced three methods: the rectangular rule, trapezoidal rule, and Simpsons rule. Today, we will focus in the order of convergence of these methods. So let me start with Matlab. Remember, always when we start Matlab, we must select the folder where we want to work. Today I want to work in this folder. Okay, so here in the current folder I can see the files I will use today. Okay, so I will start with the file called main numerical integration methods, this one. Here in this file I will try to illustrate which is the order of convergence of these methods, so how the error goes down to zero. To do that, I'm going to use a specific example with this function in the interval 0, 4 and only 5 subintervals. Okay, we are using composite rules, so I will use 5 subintervals. I will compute the approximations with the left rectangular rule, right and midpoint rectangular rules, and also with trapezoidal and Simpsons rule. In the previous session, we already coded these methods. Afterwards, we will compute the exact value of the integral. In this case, is possible, so I will do that using this symbolic variable and with this command. So this variable will contain the exact value of the integral, which I use here to compute the exact error. Okay, here is very important to say, in a real application, normally, if I use numerical integration, it's because I cannot compute the exact value of the integral. Okay, what I'm doing here is an academic example. So I'm choosing a function that I know how to compute the exact value of the integral. So I can compute the exact value of the error. Okay, just to check how these approximated values of the integral are or not good enough. Okay. So here I compute the errors. This is the error for the left rectangular rule, this is the error for the right rectangular rule, and so on. The exact value of the error is the exact value of the integral minus the approximated value of the integral with each of the approximation methods. After this, I will print the results on the screen just to see what we get. So I will just run the code up to here, okay? And we will see that we have different approximated values for the three rectangular methods, 5.8, 5.2, 5.6. For trapezoidal rule and Simpson methods, we obtain this approximation. The exact value of the integral is 5.65. Okay, we can see that Simpson's rule is closer to that value. Okay, we are using 5 subintervals for all methods, and Simpson, of course, is giving us the better precision in the solution. Now, here I'm showing you a table with all the approximated values of the integrals and the errors, and we can see here that left and right rectangular approximation have the highest error, then midpoint and trapezoidal approximation have the same they have the same order in the error, 0.0 something, yeah. But the best is Simpson, is the one that gives us the better precision in the solution. Okay, this is when I use n equals 5 subintervals. Okay, now what I can do is I will try to make a prediction. I will try to predict the value of the error when using the double number of intervals. So let's say I used n intervals, but now I decide to use 2 times n intervals, and I want to make a prediction of the error. I know that using left and right rectangular approximations, the error is going to be divided by 2 because they are linear methods. However, with the midpoint, rectangular, and the trapezoidal rule approximations, the error is going to be divided by 2 to the power 2 because they are second-order methods. Second-order methods. And finally, with the Simpsons rule, the error is going to be divided by 2 to the power 4 because we know it's a fourth-order convergence method, Simpsons rule, okay? So I can make prediction of the error just taking the error by using just n intervals and dividing by 2, 4, or 16 in each of the cases to make a prediction of the error when using 2 times n intervals. In this case, I can check with the exact errors. So I can see if this is a good prediction because I can compare the prediction with the exact value of the error when using 2 times n intervals. That's what I'm doing here. I'm calling again all the methods, but now with 2 times n intervals. In this case, n was 5, so this means this is going to be 10, okay? And I will compute again the exact value of the error, and I will display it on the screen. So let me run this part of the code. We can see here the, let me see the exact errors. Yeah, the error prediction when using 2 times n intervals and the exact errors. Okay, so we run and okay, this is the display. The error prediction when using 2 times n intervals is minus 0.1. The exact error is minus 0.12, okay, but they are very similar. Yeah, it's a good prediction. For example, for the right rectangular approximation with 2 times n intervals, we get 0.19. The exact value is 0.17, okay? For the midpoint rectangular approximation, the prediction is 0.011, yeah? And the exact value is minus 0.0110, okay, so it's a very good approximation. You can see it by your own that we get, the predictions are very good compared to the exact value of the errors, yeah? And of course, we can do exactly the same with, for example, instead of 2 times the number of intervals, 10 times the number of intervals. Yeah, for example, here I'm just plotting the same thing, but with 10 times the number of subintervals. So in this case, the linear methods get divided by 10. The second order methods get divided by 10 to the power 2. And Simpson gets divided by 10 to the power 4. So 10,000. Yeah? The error is divided by 10,000 when I multiply by 10 the number of used subintervals. Yeah. So let me run this and let me show you the prediction in the errors and the exact value of the errors that I compute with 10 times the number of subintervals. And we can see that the error prediction for the left rectangular approach is minus 0.02, which is a good prediction. For the right rectangular, the same. And we can see here, for example, that Simpsons rule prediction is minus 0.00123456 zeros here, which is exactly the same order of magnitude as the exact value of the errors. Is a very good prediction of the error. Okay. So what we have seen here in this program is that left and right rectangular approximations are linear methods. That means that the error gets divided by the number of subintervals. So if we multiply it by 10, the number of subintervals, we divide by 10 the error. Okay. Instead, second order methods, if we multiply by 10 the number of subintervals, we divide by 10 to the power 2. Yeah? Fourth order methods, then we divide by 10 to the power 4. Yeah? So this is what I wanted to explain about this file. So now let's do an exercise. let's open the file exercise, main exercises. Let's do exercise 1. It says consider the function sine of x plus 1 in the interval 0, 4 and compute the values of n. Of course, they will be different for each method, such that the left rectangle, trapezoidal, and Simpsons rules have a predicted error smaller than 0.00001. Okay, so in order to do this, we need to consider this function is exactly the same function we were using in the same interval, okay? And we want to make a prediction, okay? So let me start with the method with n equals 5. Let's compute the approximations with n equals 5, the exact errors, okay? And maybe we can print the results on the screen of these exact errors. Okay, I want to copy this. Sorry, I wanted to copy this and paste it here. Okay, now we can run it. And we can see here for all methods, which is the error we have associated. Yeah. Now, what we want to do is we want to know for the left rectangular approximation, I need to divide by a number, let's say x, such that the 0.21 divided by this number is smaller than 0.000. How many zeros? Let me check. Oh, sorry, not this one. This one. So, okay, 4 zeros and a 1. Yeah? So, what we want to do here is to find the value x I want to divide is 0. Well, the error, I can copy this value. Yeah. Times this value. Yeah, if we do this, oh, sorry, one minute. Okay, so what, oh, sorry, this is not correct. Okay, so I want to divide 0 point, the error, divided by the value I want. And if I do this, I need this number of, this is the number I have to multiply the subintervals. So that means for the left rectangular rule, this value x is the n we are compute the value of n that we need to use. Okay, so if I used n equals 5, here I have to use x times n to obtain an error smaller than this. Okay, so the minimum value of n is x times 5, because initially here we were using n equals 5. Yeah, so let's check that. If I use the left rectangular rule, with this value of x. Well, the problem here is that this is not a natural number, but I can do this floor of x. Okay, floor of x will give the it will cut this number here, but if we need to, yeah, maybe it's better to use the sale, which will round the number to the next integer. Okay, so I will use sale of x times n. Okay, I will use this value, and then I will compute again the error, which will be the exact error in this case. Okay, of course here we are guaranteeing that the predicted error is smaller than 1 to the minus 5, but this is the exact error, so maybe this one is not smaller than, but it should be very close. Okay, so let's check this. Okay, and we can see that the exact error is a little bit greater than 1e minus 5, but is very close to this value. Okay, what we did here is to guarantee that the predicted error is smaller than 0.0001. Okay, so this is for the left rectangular rule. The right rectangular approximation is exactly the same because it's a linear approximation. Now, for example, for the midpoint rectangular approximation, what we know is that it's a second order method. Yeah. So in this case, what we know is that x squared, let's say, yeah, equals this the value of the error. I have to check which is the value of the error for the midpoint rectangular approximation. Okay, for the midpoint rectangular approximation, this is the error. I want it to be smaller than 0 than this value. Okay, so x squared is going to be equal to this. So if I want to compute x, okay, I can find a new variable. X is x squared. It's the square root of x squared. Okay, so now I can call, for example, the midpoint rectangular rule. And now I need to know which is the minimum value of n. The minimum value of n in this case is 5 times this x we computed. So I will use here again the sale of x times n. Okay. Here I will not write the semicolon, so we will see which is the value of x in this case. Okay. So we can compute this, and then we will compute also the error for this method. Okay. And that's it. So for this case, for the midpoint rule, we need to multiply n by 68, in fact, yeah, because we choose the next one, in order to guarantee that the predicted error is smaller than 1e minus 5. And we can check here that the exact error is close to this value. In fact, in this case, it's a little bit smaller than 1e minus 5. Okay. Now we can do, for example, Simpsons approximation. Yeah. For Simpson, what we obtain is x to the power 4. yeah, equals the error of Simpson, is this value. Oh, sorry. Okay. And we want to divide this, we want to divide this by the error we want, yeah? And in fact, the x we are looking for is, okay, I know that this is x to the power 4, so I need to compute 1 over 4, yeah? So now I can call Simpsons rule, but in this case with the sale of x times n. And I can compute the exact error just to check is similar to the predicted error. Yeah? Okay, I want to see the value of x, so I will take out this semicolon. So if we do this, we can see that in this case x is only 2. Okay, we will use 3 because it's the next integer. We just need to multiply by 3 the number of subintervals to get a predicted error smaller than 1 minus 5, than this number. But in fact, the actual error is even smaller than that. Yeah? Okay, so this was the first exercise. Now, second exercise says, let's consider the function, a different function, okay, the exponential of x power 3 in the interval 0, 1, and compute the approximated value of the integral with all the used integration rules with n equals 100. And then make a prediction of the error for all the methods when n equals 200. Okay, so in order to do this, it's very convenient to use this file we were using before. So I will copy this part. I want to use all the methods. I will compute the errors. And also I want to make a prediction, not with 2 times n intervals, but with different values. But this is going to be useful. Okay, and these are the exact errors. Okay, so I will just copy this part. And here, in order to make it easier for me, I will comment the first exercise, which we already did. Okay. Okay, now this second exercise, a different function is given, exponential of x to the power 3. So here, this is the exponential of x to the power 3. The interval is different, it's from 0 to 1. And we want to compute the approximated value when n equals 100. Okay, so 100. Then we will call all the methods with this value of n. We'll compute the errors. And this is not necessary. It's not asking us to compute the errors. So we can comment this part. Okay, but we want to make a prediction of the error, so we really need to compute this. Sorry, we need to compute. Sorry, we need to compute the errors because then we use this to make the predictions when using 2 times the number of subintervals. They are asking us to make a prediction when n equals 200, which is 2 times the number of initial subintervals. Okay, so here we are making the prediction when using 2 times the number of subintervals. And what's going to happen is that linear methods will get the error divided by 2, quadratic methods will get the error divided by 4, and Simpson, which is 4th order method, will get the error divided by 2 to the power 4. Okay, so we can run the code as it is, and we will see the exact values. Here in this table we can see better. for this problem, which is the exact value of the integral is 1.3, the different approximated values for the different methods, and the errors. Okay, these are the exact errors. Now here what we see is the prediction of the error for 200 intervals. Remember, n equals 100. So these are the predictions, and they are pretty close to the exact errors when using 2 times n subintervals. Okay? Okay, so this is the second exercise. Now, I want to explain a little bit more about convergence graphs. So let me show you this file, main convergence trapezoidal. This code will show the convergence plot for the trapezoidal rule. I use this function in this interval, and I will compute the error for this integral for different values of h. Okay, so here n is not anymore a scalar, but now is a vector. It's a vector that goes from 10 to 500 in the steps of 10. So for different values of n, I get different values of h. Now h is a vector. It's b minus a. This dot is very important. Divided by n. N is a vector, so I need to use the dot here in order to have sense this operation. Okay, I want to compute for each one of the components of this vector. I want to compute b minus a divided by that component, and I want to store that in this vector. What I'm going to do is I will compute the error for different values of h. Okay, let me run just up to here. So you will see I will use all these different values of h. Yeah? They are getting smaller, smaller, and smaller. Yeah? And I want to check that as h goes down to 0, the error also converges to 0. And I want to check how fast that happens. Okay. Here, iter is the length of n, is the number of different values of h I will consider. Here I compute the exact value of the integral, and here I make a for loop. This for loop starts at I equals n and up to iter. And each time it calls trapezoidal rule for a different value of n. Now, this ni is a scalar value. It takes the component I in vector n. So first time, it will take the first value in vector n, 10 in this case. Second time in the for loop, ni will be equal to the second component in vector n, which is going to be 20, yeah? And so on. And now this is a vector that will contain the exact error of the approximation. After this, I can make a plot of the error, which is stored in this vector, versus h. If I do that, I will obtain a plot like this. Let me show you. Here, this is the trapezoidal rule. I know it's a second order method. The meaning of a second order method is that when the error depends on h, and it depends on h like h to the power 2. So it's this big O notation means this is equal to a constant times h squared. Yeah? So when I divide by 2 h, the error gets divided by 4. Yeah? Here I'm plotting the error versus h. We can see that is a linear method, and that when we divide by 2 the value of h, the error is divided by 4. Okay, it's a second order method, sorry. Okay, but here is very difficult. I mean, I know this is a parabola. I know this must be a parabola, but visually it's very hard to say. That's why we never use this type of plot for convergence, but we use logarithmic scale. Instead of using the common plot, h and the error, we use the command log h and the error I want to plot. So here what we are plotting is the logarithm of h versus the logarithm of the error. And the good thing about this is the following. You know that the error is c to the h to the power 2 because it's a second order method. But if I apply logarithms here, the logarithm of the error equals the logarithm of this. And by properties of logarithms, I know that the multiplication here is a sum here. And I know, again, by properties of the logarithm that these two can be written here, yeah? So finally, logarithm of the error, which is my y-axis, okay? My y-axis equals logarithm of the error, is equal to 2 times the logarithm of my x-axis plus c. So in fact, this is a line with a slope 2. So if the method is well coded, its convergence in logarithmic scale must be shown as a line of a slope 2. Here, I plot a line with a slope 1 and a line with a slope 2, just to compare and to show you that the convergence of trapezoidal rule is parallel here to this line with a slope 2. So the convergence graphs are always shown in logarithmic scale because they are more convenient. We can see more clearly which is the convergence. Here is a line with a slope 2 because it's a second order method. Now we can do the same with Simpson. Here I have pretty similar code where the only difference is I call Simpson instead of trapezoid, the rule, and I make the plot here, yeah, of the error versus h, but also I plot the logarithm of the error versus the logarithm of h. Yeah? So let me run this. And in this case, we can see here, I'm plotting a line with a slope 3 and a line with a slope 4, just to show you clearly that Simpson is a fourth order method, because we can see it's parallel to this line with a slope 4. Yeah? Here we can do exactly the same derivation, and we can see that in logarithmic scale, the logarithm of the error is 4 times logarithm of h plus c. So this means in this plot I must see a line with a slope 4. That's what we see. So that means that the method is well coded. We have the convergence we were expecting. And finally, I can show you something pretty similar with rectangular rules. In this case, I compute with the left, right, and midpoint rectangular rules. We compute the errors for all these methods. So instead of one single error vector, I have 3 different vectors because I have 3 different methods. So when I do the plotting, I plot h versus the error for left rectangular in red color. Then I plot h versus the error in blue color. And then I plot h versus the midpoint rule in green color, yeah, just to make them different and see what we are plotting. So let me run this code just to show you in this case what we get is the following. Here we can see that in figure 1 it's very difficult to know which methods are first order, which methods are not. In fact, all of them are they seem close to a line. Maybe this one, maybe we could expect it to be a parabola, but it's very hard to say here. It's almost impossible to check visually. However, in this figure, in figure 2, it's very clear. It's very, very clear. Left and right rectangle are a line with a slope 1. It's parallel to this line with a slope 1. However, the midpoint rectangle rule is parallel to this line with a slope 2. So here is very clear that the midpoint rectangle is the second order method. Okay? Okay, so let's do now exercise 3. The exercises I want to do for you. Okay, so this is done. This second exercise is also done. I will comment. So let's do now this exercise. Show in the same figure the convergence in logarithmic scale for all the used integration rules with the function f of x cosinus exponential in the interval 5, 7 with n between 10 and 300. Okay, so we have to show in the same figure the convergence graphs for all the used integration methods. In order to do that, I will start this one. So in the same figure, for all the used integration rules, okay. So I will start with this file where we compute for all the rectangular rules, okay. I will copy this here. We know that the function now is different. Instead of this function, we have to use cosinus of x times the exponential of x in the interval 5, 7. And n should go between 10 and 300. Okay, so between 10 and 300. And in this case, we don't need the plot of the error versus h. I will just keep the plot in logarithmic scale. Okay. But now this only contains the rectangular rules. I want to incorporate in here trapezoidal rule and Simpsons rule. Okay. So in order to do that, I will call here trapezoidal rule. I can see here is called trapezoidal rule. Okay. Trapezoidal rule. And I will call also Simpson. I see here is called Simpson rule. I know they have the same input variables, okay? And then I have to compute the errors for trapezoidal rule. And the Simpson rule, sorry. Okay, so for the Simpson rule, I have to use this value. Okay. So now plot. I need to plot not only the left, right, and midpoint, but also I want to plot trapezoidal and Simpson's rule. Okay. If I write this help plot, we can see here different colors and different symbols and different types of lines we can use to make the plots. Okay. So, for example, I used already red, blue, and green. Red, blue, and green. I can use cyan, for example, to plot the error for the trapezoidal rule. Oh, sorry, first H, okay, versus the error for trapezoidal rule, which is called like this, okay. And I will make this plot using cyan color. Which symbol we can use? We already used the circle and the square. We can use an X mark. I will use an X mark and a solid line. Okay. And finally, I will plot H versus the error for the Simpsons rule. And in this case, we will use magenta, for example. Magenta, and we can use which type of symbol? Star? Did we use a star already? No. So we can use a star and solid line. Okay. What else? Here we are plotting the line with a slope 1, the line with a slope 2. So it would be a good idea to have also a line with a slope 4, yeah, because we are also plotting Simpson, which we expect to have fourth order convergence. So which color? This is black, so I will use black. All the lines are black with different type of line. We already used dotted, we already used dashed, so we will use dash dot. Okay, dash dot is like this. Okay, so 3 different lines, linear, slope 1, slope 2, slope 4. So here in the legend, we have to add the things we added to the plot. Left, right, and midpoint rectangle. Then we added here, trapezoidal rule, and I will add it here. We added also Simpson rule. Okay. And what else? Yeah, then we plot the line with slope 1, the line with slope 2, and finally we plot also a line with a slope 4. Okay, and we don't need to change this. We could add an explanation for the order force, but okay, I will do it. It's very simple. We can add here that when we have an order 4 method, then this is a line with a slope 4. Okay. Maybe I will just take this out. It will be simple. Okay. So I think that's it. Let's try to run it. Oh, something happened. Let me check. What's the problem? Says the problem is here. Okay, let's read carefully. File, line, column, expression or statement is incorrect, possibly imbalanced, parentheses, or this. Okay, in this line, I start the parentheses here. Well, that the best we can do is to use this dot 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 This means the line continues in the next line. Okay. Dot, dot, dot means, okay, that was missing. This dot, dot, dot was missing. This is telling Matlab the command continues in the next line. Okay, that was missing. It's good to use this command in order to have shorter lines. Okay, it's not a good idea to have so long lines. Yeah, like this is better. And we see when I use this command, Matlab knows it must continue in the next line reading the command. Okay, so let's run again. Oh, again, something is wrong. The lengths, vectors must be the same length. Okay. Sorry. So the error says in line 190, vectors must be the same length. Okay. So let's check if they are. What's the problem here? This H versus this one, H versus this one, H versus this one, and H versus this error. Okay, I see the problem. You see, I did not initialize the vectors for trapezoidal rule and Simpsons rule, and maybe that was the problem. Yeah, to initialize this. Okay, let me write here clear all, close all, and CLC to clear all the workspace variables, to close all possible open figures, and also to clear the common window. Let's try again. Okay, now it seems it's working, and we can see the figure. Here we can see in the black color, line with a slope 1, is this one. Line with a slope 2 is this one. And the line with a slope 4 is here, okay? It's very clear that left and right rectangular approximation have the same convergence, and they are parallel to this line of a slope 1, so they are a linear method. That's very clear from this figure. In the trapezoidal midpoint rectangular rule and trapezoidal rules, both of them have second order convergence. They are parallel to this line with a slope 2. And it's also very clear that the most precise method is Simpsons rule, which is a fourth order method, and in this case is parallel to this line with a slope 4. Okay, so we can see very clear in this convergence graph with logarithmic scale. Okay, so this is this exercise. Now let me comment this exercise we already did. And let's go to the last exercise I want to solve with you. Okay, this last exercise says, code a modification of the midpoint rectangular rule. Instead of using the midpoint of the subinterval, use the point at a distance 1/4 from the left of the interval. So instead of using the midpoint, use this other point, which is at a distance h/4 from the left side of your subinterval. And then there's a question for us. Which is the order of convergence of this method? Okay, so let's first code this method. I will start opening the midpoint rule because it's pretty close to this method. So let's open the midpoint rule method. Midpoint. And I will save as, instead of mid, let's call it quarter rectangle rule, okay? So here it says function name is known to Matlab by its file name, quarter rectangle rule, so fix this for me, and it will automatically change the name here. It's very important that the name of the file and the name of the function, they must be the same, okay? Now, the main difference between the midpoint rule and the quarter rectangle rule is this point here. Instead of the midpoint, we need to use, instead of the midpoint, we need to use different formula here. We need to use the point that from the left side of the interval, which is xi, it's h/4 distance to this point, okay? So basically this is the modification. Now, instead of evaluating the function at the midpoint, I evaluate the function at a point that is a quarter of the distance from the left side of the subinterval. So I save this, and the method is called quarter rectangular rule. And we need to answer this question, which is the order of convergence of this method. Yeah? So in order to do that, which is the order of convergence of this method, maybe we could use the convergence for rectangle rules. Let me copy this here. But instead of just using the left, right, and mid rectangle rule, let's plot what happens instead of the mid rectangular rule if we use the quarter rectangular rule, okay? So here we compare left, right, and quarter rectangle rule, left, right, and the result of the quarter rectangular rule. So in this plot, this is not going to be anymore the midpoint, but the quarter rectangular rule. And the same here. And let's check what happens if we run this. Well, first figure is very hard to say because it's not in logarithmic scale, so that's not very nice. Here we can really see what's going on. And what's going on is that left, right, and quarter rectangular rule, all of them are parallel to this line with a slope 1. So when I change the midpoint to a different point here, this point that is a quarter of the distance from the left side, we lose the second order convergence and we get just a linear method. Okay, so the quarter rectangle rule is a linear method as the left and right rectangular rules. Okay, so what we can answer here is that the order of convergence of this method is linear. Okay, it's a linear method. And that's all for today. See you in the next video. Bye bye.